yesterday I started a discussion of the non-perturbative gravitational path integral and gave you a very quick sketch of many, many problems that arise when you try to make this kind of quantity, which you can formally relatively easily write down, this famous sum over histories, if you want to make this well defined. And I kind of, what we'll be doing for the remainder of the lectures will be to look at a kind of a specific class of models and see how these issues get addressed in the concrete context of this class of models. And one thing they have in common is that the geometries that enter in the path integral, they are regularized in a particular manner. I already emphasized, I mean, you do need a regularization. You're just writing down a very ill-defined functional integral at the best of times. So you have to do something, at least at an intermediate stage, to control the divergences and singularities this object is inevitably going to have. Okay, now we were getting started on understanding how you can describe curved spaces, curved spacetimes, in an approximate way without introducing coordinates. And kind of the old and beautiful idea behind this was really to think of the space as piecewise flat. So and there is no really one way of doing it, but it just turns out that a very convenient unit are triangles, flat triangles, or higher dimensional generalizations of these triangles. I mean, you could just as well use other building blocks, so there's not really anything very fundamentally significant about using triangles. You could just as well, say, take squares in 2 dimensions and approximate curved spaces by gluing together squares of this way. What is nice about triangles, and that is why kind of triangulations make an appearance all over the place, for example, in producing animated movies, they very nicely and kind of with a reasonably small number of building blocks approximate curved surfaces. And if you take squares or pentagons, well, on a very local scale, they're much more bumpy, if you like. So these triangles explore in a quite efficient way curved spaces, but that's just not a matter of principle, it's just a matter of practice, if you like. So one question, so what are the degrees of freedom? In general, we have in gravity. Well, it's the local curvature degrees of freedom. And we usually just express this, via some curvature tensors which contain second-order derivatives of the metric. And the question is now, how do these curvature degrees of freedom, how do they get encoded into these triangulated spaces? And again, let us look at the 2-dimensional case, because it's the one that is easiest to visualize. What we'll be looking at is a curvature property that goes by the name of Gaussian curvature, and I'm sure you've seen this various times before in your GR courses. Now, for the particular case, where I'm gluing now together a triangle, say, in 2 dimensions, this is the same, it turns out, as what one calls the deficit angle. Now, what is a geometric situation, say, in 2 dimensions? You glue together a bunch of triangles. Well, they can have any edge length, really. So let's imagine we are just trying to approximate a curved Euclidean space of positive definite signature. Now, sorry, these are supposed to meet in a single vertex here at the center. And let me just demonstrate here. It's my little piece of paper. So here I have for you a special case. So they're all equilateral triangles. And so 60-degree angles. Now, I can use them clearly to tile the flat plane isometrically, right, by gluing these together in a regular tiling like this. So around each vertex, just 6 of these meet. And just that means it's flat. But of course, I mean intrinsically flat, not as viewed from the outside. That is not a quantity that interests us particularly. So it's intrinsically flat, and the way to understand, if you were a two-dimensional being that lived in this surface, would be through parallel transport. Okay, so if you parallel transport, a vector along any closed path, it will return to the same position. Now, this is different when now at this particular given vertex, say I cut out one of the triangles, so that just five equilateral triangles just meet at this point. Now, there is now curvature at this one point. That means any parallel transport, any path that winds around this kind of singular point exactly once, the vector will experience a rotation by 60 degrees. Okay, so that's the way to, in an intrinsic way, to uncover that you are living in a curved space. Of course, there are various other ways, but I mean, parallel transport is kind of the canonical way you learn about when you study general relativity. Of course, if I cut out two triangles and glued this together, I would pick up more curvature. And this is exactly, because this is two dimensions, this is what one calls the Gaussian curvature. So of course, it's a special case, there's a singularity, but I mean, it works the same way. So you discover it, uncover it by parallel transporting a vector. Conversely, of course, I might insert additional triangles. Then I would generate something that looks, I mean, from the embedding picture, like a saddle point or something. That's also possible. Then you don't get a deficit angle, so it's nothing that's missing to 2 pi, but you get an excess angle. And this is also, that's Gaussian curvature of the opposite sign. Okay. So the formula here, in general, when we look at these triangulated geometries, say in 2 dimensions, for this deficit angle, this is given by 2 pi. So 2 pi is the flat case, right? Nothing happens. Minus, sorry, I'm saying this wrong. 2 pi, now I'm subtracting something. Now I'm subtracting the angles that meet at this given vertex. So this is in 2 dimensions, 2 pi. So now these are those building blocks that share what is called, this is called a hinge. In 2 dimensions, it's simply a vertex. So in 2 dimensions, it reads at the angles that belong to the building blocks which contain that given vertex and subtract them from 2 pi. So let me call these alpha I. So this is alpha 1, alpha 2, alpha 3, alpha 4, alpha 5. Now imagine, now I have to spread this out because I have to draw it on the blackboard. Now imagine the situation was such that actually, well, this here was identified with that. And what I had to do in order, to put it into the plane, I had to cut it open. And what is then left here is exactly the deficit angle delta. This is just what is missing to 2 pi. So this is delta in this case. This would be delta. Of course, assuming these should have the same length. Otherwise, of course, I'm not able to glue them together. So let's make this a little bit longer. So they have to fit, of course, here. So this is the same delta. In general, this I here kind of will label a D simplex when we are in D dimensions that labels D simplices sharing a D minus 2 simplex, and that is the so-called hinge H. Now the reason why it's called hinge, is more obvious if you go to 1 dimension higher. In 1 dimension higher, you're looking at flat three-dimensional tetrahedra. And what you then have to do, you glue them together, and in that case, the curvature will be concentrated along one-dimensional edges. Right? So you have a given edge, and then you consider, well, a bunch of, now I have to draw this properly, like a bunch of tetrahedra that meets around this such an edge. So this would be an edge. You see, that is kind of a single tetrahedron, but now I'm gluing all around. I'm gluing a bunch of tetrahedra. And again, the geometric data are just given in terms of the edge length. And I can, of course, compute also here all these angles once I know what the edge lengths were of these triangles. Okay, so these are data, geometric data that are given to me. I add them up and subtract them from 2 to pi. Here in higher dimensions, I do the same. I mean, I have now, of this tetrahedron that shares this wedge H. There is, of course, an angle when I go now. I mean, there's a parallel transport, would not mean I run around such a hinge in this manner. And there are of course, more tetrahedra, so I can make a full tour of this, walking around this one-dimensional link. So, and that is generically the case. So what you get by gluing together these triangular building blocks is, in general, a curved manifold, where, however, the curvature only appears at simplices of codimension 2. So in 2 dimensions, curvature is just located at vertices. It's like in a delta function-like way, because you see, if I do any other parallel transport that doesn't contain this one vertex, it will always come out to 0, the deficit angle. Okay. So this has to be in there. And in higher dimensions, in 3 dimensions, the curvature is located along the one-dimensional edges of the triangulation. In 4 dimensions, that is the case that interests us, because it's a little more difficult to visualize. Then you pick out a triangle, and look how many, look at the four simplices, that share this one triangle. And again, you walk around a triangle and pick up angles in this manner and compute with each triangle you can associate a deficit angle. And of course, one of the points being that the deficit angle can be just expressed as a function of these length variables. So this is how I said the triangulation is in general given to me. I have to tell you how the triangular building blocks are glued together, and I have to assign, in a consistent manner, link lengths to all the edges of the triangulation. And that will enable me to compute the alphas, and from that I can then compute all these deltas. So in the case that sum over alpha I is equal to 2 pi, then of course, locally, my space or my space-time is flat. If the sum over alpha I is smaller than 2 pi, I obtain a positive Gaussian curvature. So the Gaussian curvature is, of course, what is the intrinsic property of curvature of 2 surfaces, which you introduce when you study geometry of 2 surfaces. But it generalizes, of course, it generalizes to kind of 2-dimensional submanifolds of higher dimensional curved spaces. Now, one thing we still have to do, because what we want to get at is an expression for the path integral. And of course, path integral, the prescription is, with each geometry, I have to associate an e to the I action associated with this geometry. So what we still have to do is we have to find an expression for that action that depends on these length data. And, well, we're lucky that has been done a long time ago, again, by Regge. So what we need to do is to rewrite, say, the Einstein-Hilbert action, which depends in the continuum on these typically, smooth geometries. So we have to extend that to the case of these piecewise linear objects given by a triangulation and a bunch of length assignments. And the expressions here, so we are interested, first of all, of course, in the integral of the scalar curvature, the Regge scalar over the manifold, and for generality, a volume term. So that gives me then a cosmological term contributing to the action if I multiply the 4 volume by cosmological constant lambda. So these two things I need to know how to write in terms of these quantities and in the absence of coordinates. So that's the first one. So that's just simply the d-dimensional integral of the Regge scalar. Also, this works for any signature. Of course, we would usually be interested in kind of the minus plus 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 signature. So this here becomes, on a given triangulation with given line, with given edge length assignments, it becomes the following. It's these deficit angles enter, and you're summing over these hinges h that appear in this formula. So I now labeled them I. Please don't get confused with the notation over there. So the hinges, the d minus 2 simplices at which the curvature is located, their volume enters into this formula and multiplies kind of the deficit angle. So this just goes to say it's essentially, well, see, this is how you compute the deficit angles. And now what you're doing is, say, if you were in 2 dimensions, you would sum over all vertices and just add up the curvature contributions associated with every one of the vertices. And in 2 dimensions, well, this would just be the volume of the vertices, which by definition you put to 1. Right. So what you then get in 2 dimensions is just a sum over the deficit angles. And that just is the Gaussian curvature of a 2-dimensional surface. And just in 2 dimensions, this expression is exact. So in the sense that the integral of this curvature in 2 dimensions is, as you may know, it's just a topological quantity. Right? So it does not depend on the details of G mu, but the integral is fixed once you fix the topology of your 2 surface. Okay? So using this formula, where here the deficit angles appears in the way I've defined them, reproduces that exact number for the case of piecewise flat manifolds. Okay. Of course, everything is slightly non-trivial because, here these are smooth metrics, and the metrics I'm talking about, they don't lie in the space of smooth metrics, so they lie outside the space I usually consider when I just study the classical dynamics of Einstein's theory. Okay, so there is something to be said and defined here. Yes.
So in 2 dimensions, the Euler characteristic remains unchanged if I triangulate a Riemann surface.
Yes. So you can. That's what. Or you might say, yeah, it's a fixed number. This is reproduced by any triangulation I might choose. Say, any compact surface. The torus, the sphere, or of course also stuff with boundaries. Also for Lorentzian things, with some care that goes through. Actually. But this is no longer true in higher dimensions. So, and there, this expression is really then to be thought as a possible kind of discretization of the standard formula. So it's something then that you can show, well, with some provisos, goes over in an appropriate limit when my triangulations become finer and finer to this expression. So there are some theorems that exist about this, but well, I'm not going to quote in detail any of them to you. But for the purposes of the classical theory, what you always want to do is you start, say, in 2 dimensions, you see from some curved surface, and in order for this to work, you're keen on making your triangles tiny, 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 so they can, in a nice way, approximate ever better the curvature this thing has. And of course, it's clear that the smaller I make the triangles, the smaller I can make the deviations, if I choose my triangles properly, from the geometry of a given continuum object. Okay, so that is the expression for the curvature. So in integral over m, I should say here. So the other thing is completely straightforward. This is the volume term. So this is what I need when I include a cosmological constant term. So this is in the continuum just the square root of the modulus of that g integrated, and this becomes simply, in a triangulation, it becomes the sum over the simplices of dimension d that make up the manifold, the simplicial manifold. So this just means, in 2 dimensions, this is the sum over triangles, and for each triangle, I look what is its volume, and I add them all up, and then I have the volume of the 2 manifolds. So this is clearly a transparent definition.
Question?
Yeah.
If we choose another symbol, does it give the same result if we calculate the action?
No. This will just depend on these data. Well, even if you keep the same triangulation, if you change the edge lengths, it will change some of these assignments. And you will get, in general, a geometrically distinct simplicial manifold. So it's then like having two different, the curvature will be different. Now the curvature assignments.
Is this normal or weird? I think it's weird.
No, it's not weird. You see, these data substitute, they are a discrete versions of the continuum data. Modular diffeomorphisms, of course, right? So they were what became of my assignment G mu. And here you could say, look, isn't it strange? If I choose different G mu's, well, I get, in general, distinct geometries, unless they happen to be diffeomorphic in some way. So here it's the same story. You have an underlying kind of triangulation of the space, but of course, if you change these length assignments, the intrinsic geometry of this thing is going to change. Yeah.
So when you introduce the triangulation, do you break the diffeomorphism variance, or can you still have some?
No, it's no longer there, because the diffeomorphism variance, of course, it acts on smooth continuum quantities, on tensors. And it says, if I change my coordinates, well, I get some change in the tensorial entries. But here I don't have coordinates. So diffeomorphisms no longer act on these data. Okay, so it's just pure geometry. So in that sense, it's very nice. It's very close to the spirit of Einstein's theory. There is one, this redundancy, certainly for the purposes of the quantum theory, is of course terribly annoying, right? It doesn't give you any additional information, but you have, in the continuum, you have not much choice but to carry this around with you and whatever, gauge fix or invent some nice way to have this drop out, right? And that gives you a lot of trouble. So here, one chooses a different route and says, okay, let me just work in terms of geometric data. And then I don't have to factor out any redundancies from the path integral. So I just add up, and my path integral will be just a sum over distinct objects of this type. And they will almost automatically, they will all be different, I mean, in terms of the geometric properties. Yes?
So in principle, we're interested in the continued limit, though. Are we?
Yeah, this is, of course, there will be some cutoffs. So like the number, the fineness of the triangles. And of course, in the end, you want to remove this. But this doesn't mean you get the coordinates back.
No, but the different triangulation should not then matter. The error in that limit should be very small, right? And the difference between different triangulations.
Yeah, well, we come to this. Of course, one has to be careful. One shouldn't think too classically, but I'll say something more about this. So, using such objects in the classical theory. So these were invented as a tool, say, to solve the Einstein equations, numerically, for example. So then you can just try and start with data, or three-dimensional triangulated data, and then have an evolution described without coordinates in some approximate way, which you need because we know rather little about general solutions of Einstein's equations, unless they're very, very highly symmetric. So if you're in some general situations, you're looking classically for approximate ways to solve these equations. And what Regge had in mind when he came up with this proposal was only the classical theory. And there, of course, your aim will be to approximate as well as possible a given four-dimensional geometry, which is a solution to the Einstein equations usually. In the quantum theory, you have a quite different aim. You want to approximate the space of all space-times, because that is the domain of your path integral. And that is a quite different story, because you already know, I mean, your expectations are that this is not going to be dominated. I mean, we're not talking about semi-classical approximation. It's not going to be dominated by classical-looking objects. But it's going to be dominated by very, very non-classical things. It's like, the paths of the path integral, the paths that appear in the Wiener measure. There's a nowhere differentiable path. So you would have such an expectation that a similar thing happens when you want to construct a non-perturbative path integral over higher dimensional geometries, as we're trying to do. So these are two different cattle of fish. Now, okay, so what we're going to do, we'll represent our kind of continuum sum over histories, or integrals, in terms of equivalence classes of metrics. We're going to transform this into some sum and or integral over triangulations, given in terms of these data here, T, L, I. And there are essentially now two ways of doing this. So A goes by the name of dynamical triangulation. Maybe abbreviate this for later. And what you do there is you fix all edge lengths and you let T vary. So I'll explain this in a second a little more. So you fix all Li squared to one length. And okay, if you want to allow yourself the possibility, say, to have time and space-like edges, you can do it like that. And then you sum in the path integral over T, and B is a different way. It's called quantum Regge calculus. QRC. In this version, you fix a triangulation, and then you integrate over Li or Li squared. Doesn't really matter. So where did I come from? I came from a path integral e to the is g mu nu. So which depended kind of on geometries. And here I was kind of summing over geometries. So geometries were already kind of the quotient of Lorentzian metrics modulo four-dimensional diffeomorphisms. So these guys I now approximate by these piecewise linear structures. And now my task is somehow how do I, what's the way, what choices do I have? And so roughly speaking, the choices are as follows. By choosing all my edge lengths identical, it just means all my building blocks are identical. So for example, really, if I was in 2D in Euclidean signature, I would just have one type of building block. And what dynamical triangulations is then saying, well, my way kind of to sample the space of all geometries is to look at all inequivalent ways of gluing these building blocks together to obtain, a piece of curved space. Yes? So that would be version A. The other one is to say, okay, let me just start from a given grid, a given lattice. And a typical choice would be something like a divided cubic lattice, so a square lattice, something like this, where you, say, subdivide each one of these squares, right? Then you have a triangular lattice. But now, of course, there are very many ways. You can now assign edge lengths here, right? L1 squared, L2 squared. And they will generically all lead to different, intrinsically differently curved geometries, right? So that is kind of the alternative way, kind of the complementary way. And in this way, you hope to sample, to capture kind of information, well, that's in this space. Right? Of course, a priori, you're not entirely sure what in a continuum limit, how this space will be characterized. It will be presumably some space of geometries, but which geometries precisely? Certainly not the smooth geometries. That already, well, you know from your experience with kind of the particle path integral that these are unlikely to be nice or classical in any sense. So here maybe a natural thing to expect would be some set of continuous but not differentiable geometries. So this would be kind of a natural guess. But what in the end this is going to be, well, we don't know. And it's a priori not known. And in a way, what your task is to present a construction via, say, a limiting process, where you then show that certain limits of this process, when you remove the regulator, when you make the triangulation finer and finer, exist in some to-be-specified sense. And when it exists, and when you can then show it contains interesting physical information that has the right classical limit, but also makes nice predictions about whatever, quantum geometry, well, then you're done. But of course, there are many steps to be thought of. But don't think of it as too classical. So you're really doing here a non-perturbative sum. You're not just integrating over small quantum wiggles around a given classical solution. OK, now, my next step will be to explain to you that A has a bunch of advantages over B. Now, the first one of them, I'm not going to write them down. The first one is, well, that has nothing to do with advantage. It is a difference I want to point out to you. here, the dynamical variables are these LIs. And they are still smooth variables, right? Because here, if I look at any one of those, I can just make it longer. I mean, just in a continuous fashion, and thereby change the geometry. Now, these data, they are not continuous, because my way of getting from one triangulation to another triangulation, if I want to think of it as an active process, would involve kind of cutting up the triangulation and re-gluing it in some other way. So that's not a continuous process. So here, I no longer have kind of continuous variables floating around. This is why this way of approximating geometries, if I wanted to do classical theory, I wanted to do classical Einstein equations, is much less suitable. So this is much better. But for the quantum theory, as I already started to explain, we have something very different in mind. This is what we want to construct or approximate, not a single given smooth geometry. And of course, you're interested, of course, also in, well, what is the path integral going to look like in these two complementary formulations? Now, a nice aspect of this one here is that for a given, so if you fix the number of triangles or building blocks, then the path integral coming from here is finite. That means, if I fix n, so n was just the number of building blocks, just fix it to say 1,000. Then the path integral would be, I now construct all distinct geometries I can get from gluing together 1,000 equilateral triangles. And each of them are away with the Regge action. That's well defined. So the Regge action, just what I gave you here. Then this is finite. You might say, okay, well, that's just because you've regularized the thing. But it happens not to be true for Regge calculus. Because even if you have just a finite number of triangles, you will find that there are singular directions where you can scale some of these L variables to create infinities in your path integral. So then already there, you need additional cutoffs, even for a given volume. Cutoffs on the length variables L. Another thing is, and that is kind of important for doing some kind of analytical calculation. I told you, of course, that these LIs, not so nice aspect of them is that they cannot just take arbitrary values in R, because they are subjected to triangle inequalities. So whenever I have a situation like this, I get triangle equalities for every single triangle that relates the three edge lengths of that triangle by an inequality, which must not be violated. And this holds for every single triangle in here. So you can imagine you get a highly, highly coupled set of inequalities, which you have to take care of if your path integral then becomes something like a sum over all, or product over all link variables, some DLI. So then, well, this looks easy enough, but this is a bunch of L integrations, and they have highly coupled integration limits because of the triangular inequalities. Now, as a consequence, one cannot use this framework, this quantum, one can do no analytic calculations, not even in 2 dimensions. It turns out it's not a hindrance at all in doing, in simulating the path integral, but one cannot basically, unless one has tiny, tiny triangulations where one can handle these inequalities explicitly, one cannot do any calculations, analytical calculations with it. And that's not true here. So actually, if you look at these models in 2 dimensions, you can solve them analytically as statistical models, and you can determine their asymptotic properties in an extremely nice way. Of course, these are only toy models. And again, if you go to higher dimension in 3D, you can do a few things. But in 4 dimensions, you can essentially do nothing analytically, I mean, really in determining kind of analytically what the path integral is. But nevertheless, I mean, doing this in 2 dimensions and comparing it to a continuum theory and seeing that you get something sensible out is very reassuring. And this you don't even have here in a 2 dimensions theory. So, yeah, these are various advantages. So I'm now going to stick, for the rest of what I'm going to say, I'm going to stick here with this version A. It doesn't mean that this Regge, quantum Regge calculus is altogether useless, and one can talk about it. But it seems also inequivalent in the terms of the results it produces. Okay, so now what we're going to do, still have some time. So we're not now going to write down the explicit form of our non-perturbative path integral takes in terms of these dynamical triangulation data. So the dynamical, of course, refers to the fact that there's not a single triangulation I'm working with, but I allow it to have arbitrary shapes. So this is what it is. I'm using, again, the z as a limit, as a notation for the entire path integral. And now let me include already, my intention. Let me state the intention that, of course, you have it as a regularized framework, but then you want to remove the cutoffs in a systematic way. So you want to study some limits of the quantity that I'm now going to write down. So this is, now, it's a genuine sum, if you like a discrete sum, because as I told you, there are no continuous dynamical parameters involved anymore. And the sum is over inequivalent triangulations, so inequivalent kind of S geometries. And it's a very simple measure factor here, which I explain in a second, eta I S Regge of T. Now, A was my edge length. So my ultraviolet cutoff, you could say. And what I want to do is I want to make the triangle smaller and smaller and smaller in the end. So to shrink them away, really. Now, what is CT? This is kind of the size, so the number of elements of the automorphism group of the triangulation T. And I explain this also in a second. And this space curly Tn are all, well, let me specify what I, causal triangulations, so Lorentzian triangulations with no more than n building blocks. Of course, that explains exactly also why n, I want to take n to infinity. So in the end. So this here is the continuum limit. Which you want to perform, kind of keeping kind of physical volume fixed. So, well, one way of doing this is to keep a to the d times capital N fixed. So this is just what a physical picture one has. I start with something that is a chunk of space-time of a certain 4 volume. And then what I do as part of this limiting process, I keep that fixed kind of as a physical quantity to the extent this makes sense. So this should be, of course, an equality sign here. By simultaneously letting the lattice spacing shrink and taking more and more and more building blocks. So I get just a finer and finer subdivision of that piece of space-time. So now, you see, you can do this. Right. So what is your task? To evaluate this. Well, let's start with some small n. So you have n building blocks. Do things in a simple way. Start with 10 building blocks. Now, your task is to glue them in all possible ways. Now, for each of them, you compute the Regge action, which you do with the prescription up there. You do the sum over the d minus 2-dimensional simplices, and you look for the deficit angle, and you add them all up. Then, to get the volume term is just n times whatever the volume of your individual building blocks is. Now, one thing is you have to look out for is whether the triangulation you're looking at happens to have accidental symmetries. By this I mean there is a map which is not the unit map, which maps the thing onto itself. So something like an isometry. When that is the case, you don't weigh it just with e to the is, but you divide by the size of that symmetry group. So this is what the CT is. Now, is that a very relevant term? No, it's not, because it turns out this type of symmetry, and the bigger the triangulations are, the rarer become these symmetries. And this, for large n, this is almost everywhere 1 all the time. Okay, because these just, these are such complicated objects, so it's very accidental if they have such a discrete symmetry. But if you look at kind of continuum arguments, what is a measure you expect? You expect up there this curly d of g mu nu. Well, often people make an answer which involves the so-called de Witt measure. So that's also a diffeomorphism invariant measure. And it has exactly the same property. Namely, if the geometry, the argument in the integral is one which has special isometries, then it has a smaller weight in that path integral. So in that sense, this construction mirrors this property also at the level of these entirely diffeomorphism invariant objects. Yes?
You wrote causal.
Yes. Yeah. So that refers to a specific way, which I'm getting into, where, first of all, I have a Minkowskian. All my building blocks are Minkowskian. But I also have to give you rules that ensure that kind of they are glued together in a reasonable way so that I have really a well-defined causal structure on the entire thing. So that I don't, glue this together with something, where, say, the light cone goes this way, and maybe I create closed curves and other nasty things. But I give you some more details about this later. Yes?
So how will you deal with, for example, black hole spacetimes, where you have this kind of switching?
Locally causal.
Well, locally causal. Well, you have to think about, of course, again, is that a good question I want to ask here? This is more like a classical question. I have a given space-time.
No, it's just I'm worried that
yes.
Somehow you could have your horizon exactly on the line passing.
Yeah, well, it's a question, what kind of things appear? Now I specify specific gluing rules. Then you could ask the question, well, are in this big sum of very unwieldy kind of piecewise linear geometries, are they some that are kind of close to specific geometries? Or do I have to, well, I could also feed that in via specific boundary conditions. Do I expect, to be able to triangulate all the way to the central singularity of a black hole? So, of course, there are many questions one can ask. But a priori, this is a very flexible framework, I want to say. Okay. Now, so nice properties, first of all. So we are working directly on this quotient, as I said various times. So this is defined directly on, well, curly G is not really the right thing. So I should remember that I'm talking about an extended class of objects. I mean, these piecewise linear things, they are, of course, not smooth geometries. So Regge, let me call them G Regge, of some given topological manifold M. This sum is kind of manifestly finite. For finite n. And space-time is, it's still continuous. It's continuous, but clearly not smooth. Not smooth. And also, I mean, there's sometimes misunderstanding of what to call this. I mean, space-time is not discretized. I mean, it's not that space-time comes in discrete chunks. I mean, there's still, it hangs all together, like in a manifold. And it makes sense to locally say, I'm talking about a d-dimensional manifold, because that property is still present when I glue these triangles together, if I obey certain gluing rules. So if I allow wild gluing rules, then I might violate the manifold conditions. And can illustrate this, say, in 2 dimensions. If you allow, say, just triangles to be glued together like this in a point, of course, this would no longer be a 2-dimensional simplicial manifold. And you can do all kind of funny things. But usually, what one looks at here is simplicial manifolds. So what is this? What you could say is discretized are the curvature assignments, because really, if you look at kind of the sum and the way curvature appears in these piecewise flat constructions, it's just located in this delta function-like manner at subsimplices. So these curvature assignments there are discretized, or discrete, you could even say, but spacetime itself is continuous. And you can, for instance, construct geodesics on that space. It's just no problem. I mean, they just go through the building blocks. You know how light rays propagate in these things. Yeah? So that you can just, in a straightforward way, compute. As long as they don't, when they hit singularities, then you might have an ambiguity. But in general, you just know all these things. So many of the concepts from smooth manifolds still carry over to these generalized objects. Okay, so just a few remarks about this. I already said, so there is a beautiful way, if you do that now you have a prescription, and you say, well, I haven't made too many assumptions about stuff that goes in there. It all sounds very reasonable. But who knows what pitfalls are there? So it is very reassuring if this can be shown, this construction, including such a continuum limit, can be shown to reproduce, in a sufficiently simple case, a bona fide, continuum calculation to the extent that is well defined. So that is still possible in 2 dimensions, and has also, convinced people of the validity of this method. So there is a non-trivial example of this in d equal to 2, and Euclidean signature, so Riemannian, you're just summing over Riemannian curved geometries, and it goes by the name of Liouville gravity, or Liouville quantum gravity. Now, the reason being that there is a continuum treatment, that the path integral in 2 dimensions is just about sufficiently simple to be able to handle it. I mean, modulo, with some provisos, some additional assumptions, but it's still relatively easy. So you have, on the one hand, you can exactly solve this by the methods I just explained to you, so it's exactly soluble by dynamical triangulations. And there's an entirely, and in this case, you have another nice way of rephrasing. Now we have Euclidean geometry, so what you would have here would be a minus sign, so this would be a Boltzmann sum in 2 dimensions. What you have in 2 dimensions, you have so-called matrix models, which is a technique where really to write down a generating function which produces, kind of as its Feynman diagrams, all the 2-dimensional geometries, or rather graphs that are trivalent graphs dual to these geometries that appear in the path integral. So in 2 dimensions, you have a neat way, or another way even of solving these models, the partition functions. And this is why these matrix models, for which one then has special solution techniques, if they're simple enough. So this can be exactly solved by dynamical triangulations, or closely related by kind of matrix model techniques. And it also turns out to boil down to a combinatorial problem, because in 2 dimensions, you see, if I fix the topology, the curvature term is just a topological term, so it's the same for every geometry. So I can just forget about it in the path integral. So the only thing I do is I have an e to the minus lambda times 2 volume. So that's kind of all there is. And performing the path integral then boils down to counting how many ways of gluing are there for a given number of triangles. And that's a nice combinatorial problem that mathematicians have solved back in the 1960s. So you have many ways of handling this in 2D. Now there is a related, so I would say an almost exact way of treating this in the continuum. In a standard path integral way, of the path integral, where you choose a certain gauge fixing of these 2-dimensional geometries, you get, of course, everything. You get gauge fixing terms, you get a Faddeev-Popov determinant. Then you make a particular ansatz, because this model still has to be renormalized. Then you make the ansatz that kind of the renormalized, the effective action that governs the system has the same kind of terms appearing in the action. And on the basis of this ansatz, you can just write down kind of in closed form, essentially, a quantum theory, and that is due to Distler, Kawai, and others. So that is around 1990. And beautifully, these 2 things, wherever they could be compared, agreed. So there are various things you can compute propagators. You're talking about, now Euclidean surfaces, and you can look at, loop-loop correlators, so you can cut out little loops of these surfaces. So there's a bunch of natural kind of correlators you can compute in these theories, and that characterizes this kind of the physical properties of these toy models. There's no claim that their physics is realized anywhere out in nature. But nevertheless, they're, of course, kind of geometric, non-trivial geometric path integrals. And they share some of the characteristics of Einstein gravity, but, of course, in lower dimensions. So that certainly reassures you that you're not completely barking up the wrong tree with this construction. Yeah, so historically, here I've written down everything. I had written down everything in for Lorentzian signature. In particular, I had the I here. Right now, really, it started. People first used this method in 2 dimensions, and they really started with these Euclidean models, where you started with these partition functions that are just real to start with, and you just take as your starting point these Euclidean geometries. And for those, you don't have any restrictions on how you glue them. You just take a bunch of these equilateral triangles. Well, and as long as you stick with local manifold conditions, any gluings are allowed. So in this sense, they are isotropic. I already indicated to you, if I want to make this Lorentzian, well, my little triangles, there will be pieces like cut out of a Minkowski space, and they will all have a light cone structure. So in each one of those, of course, I have a definite geometric structure. I know exactly how the light rays go. And I have to glue them then to some overall curved manifolds, which still has some nice causal structures here. Now, doing the Euclidean, so that raises, of course, doing things the Euclidean way raises the issue of, well, what is the relation between a Euclidean path integral, where you're integrating, say, even, let me revert to a continuum language, where you're integrating over Riemannian 4-dimensional curved metrics, where you weigh each with e to the, well, it's a straightforward Einstein-Hilbert action you can write down for these objects. G mu nu. So how is this related? What does this have to do with the Lorentzian thing, which is what you are physically, primarily after? So IS. Einstein-Hilbert. G mu nu. So and it has already come up in questions also that I've addressed here. Well, this space here, of the kind of here one is integrating over these kind of isotropic geometries, which for instance don't know about causal structure at all, and here one is integrating over causal geometries. So these are just how should I call them? Euclidean geometries. And these are causal geometries. And these are quite different animals, and there's a priori absolutely no reason why there should be anything like a 1-to-1 correspondence, even at the level of the domains of the path integral. Okay, so then the issue is, well, what is my starting point? And I don't have any nice, in general, I don't have any nice Wick rotation, as I promised you will see in one of the exercises, to map me from one to the other. When I'm on standard, when I'm doing quantum field theory on Minkowski space, of course, I'm interested, this is much easier to compute, and its convergence properties are much easier to discuss than those of these integrals over amplitudes. And I'm often, for instance, when I do standard quantum field theory on a flat lattice, one always looks at this quantity, because otherwise you can't even set up your computer simulation if you have complex weights. So you're forced into computing on this side. But in that case, you have just a set, you have just a theorem that tells you under what circumstances there is a nice analytic continuation of the results you obtain for your endpoint functions back to the physical Lorentzian signature. And this goes by the name of the Osterwalder-Schrader axioms. So that underlies our nonchalance, often in quantum field theory on flat space, of going back and forth between a Euclidean picture where you work with imaginary time, and one where you work with real time. So it's t going to it. And the justification for that is a theorem that tells you, well, you can do that. When you do the analytic continuation, you're not crossing any singularities in the complex plane, essentially. What becomes of that on a general curved space, fixed space, not even that is entirely clear, but certainly we are interested in an even larger generalization, where we are interested somehow in summing over all curved spacetimes of a signature, Euclidean versus Lorentzian. And we are interested in, well, what kind of, is there any relation at all between those things? OK, so on this deep point, let's stop. And I'll meet you again tomorrow.